Ever wondered how we know what molecules actually look like? I mean, we can't see them, right? But scientists have figured out a way to draw their blueprints. And today, we're going to crack the code on those blueprints. They're called Lewis structures, and they are basically the maps to the entire invisible world of atoms and electrons. And you know what? We're going to figure them out together.
So that's the big question, isn't it? How on earth do you draw a map of something you can't even see? How do you predict the super intricate ways that atoms connect and share these tiny little particles that make up, well, everything?
They do it with a diagram that looks just like this. This one's for carbon tetrachloride. And yeah, at first glance, it kind of looks like a secret code with all its dots and lines. But every single dot, every single line has a very specific meaning. And it's all dictated by a surprisingly simple set of rules. And I promise, by the end of this, you'll be able to read and even write this language yourself.
Okay, so to crack any code, you first have to understand the why behind it. Why do atoms even bother bonding in the first place? Well, it all boils down to one single, really powerful idea. This is it, the octet rule. You should think of this as the ultimate goal for pretty much every atom out there. They want to have a full outer shell of electrons, which, for most of them, means having 8. We call these outer shell electrons valence electrons, and honestly, they're the superstars of all of chemistry. A full shell is like an atom's happy place, its state of maximum stability, and atoms will do almost anything to get there.
And here's what's so cool about how they do it. In molecules, atoms don't just steal electrons from each other. Nope, they cooperate. Just look at water here. The 2 hydrogen atoms and the 1 oxygen atom, they all pull their valence electrons together. They share them so that each atom in the group feels like it has a full shell. It is the ultimate chemical teamwork. And you can see there are really 2 main ways to get to that full shell. On one hand, you have ionic bonds, where one atom literally just gives an electron to another. It's a total transfer. But on the other hand, you have covalent bonds, and that's what we're focused on today, where it is all about sharing. That sharing is what creates all the molecules that make up you, me, and the world around us. And if you want to see what that ultimate stability looks like, well, look no further than the noble gases. You know, helium, neon, argon. These guys are the VIPs of the periodic table. They're just born with a full outer shell of electrons, so they have absolutely no reason to bond with anything. They're perfectly happy all on their own. They've already won the game that all the other atoms are trying to play. All right, so now we know the why. Let's get into the how. Building a Lewis structure is actually a super logical step-by-step process. It's all about mapping out exactly how these atoms get to that stable state. And it all begins with a simple count. We're going to follow this simple 3-step game plan. First, we figure out our electron budget. We count up all the available valence electrons we have to work with. Second, we arrange the atoms into a basic skeleton. And third, we start spending that electron budget, distributing them to form bonds and make every single atom happy. Now, step 1 is way easier than you might think. You don't have to memorize a giant list or anything. You just need a periodic table. See, an atom's group number is basically a cheat code that tells you how many valence electrons it has. If an element's in group 1, it has 1. Group 14, it has 4. Group 16, it has 6. It's an awesome shortcut built right in. Okay, let's put that into practice. Let's take carbon dioxide, CO2. So carbon is in group 14, which means it brings 4 valence electrons to the party. Oxygen is in group 16, so it brings 6. But wait, we have 2 oxygen atoms, so we have to multiply its contribution by 2. So you add it all up, 4 plus 12 gives us a total budget of 16 valence electrons to build our whole structure. But what if you're dealing with ions, molecules that have an overall charge? Well, the rule is super simple. The charge just tells you how to adjust your electron budget. If you've got a negative charge, like the carbonate ion with a 2- charge, you've got extra electrons, so you add 2 to your total. If you've got a positive charge, like the ammonium ion, you're short on electrons, so you take 1 away. Easy enough, right? Okay, we've got our electron budget. We know exactly how many we have to work with. Now we need the actual blueprint. It's time to arrange the atoms and figure out who goes in the middle and who's on the outside. So here's the main rule of thumb. The least electronegative atom, that's the one that's the least grabby for electrons, usually gets to be in the center. A really quick way to figure this out is to just find the element that's farthest away from fluorine on the periodic table. But there is one golden, unbreakable rule: hydrogen. It is always on the outside, no exceptions. It's just too small to be anywhere else.
So let's apply this to our water molecule, H2O. Well, we know our golden rule. Hydrogen has to be on the outside. That only leaves one other atom, so oxygen must be our central atom. So our skeleton starts with oxygen in the middle, and we just connect it with a single line, a single bond, to each of the two hydrogens on the outside.
Okay, we've counted our electrons, we've built our skeleton, now it's time for the grand finale. This is the most important step, distributing our electron budget to give every single atom that stable, full outer shell that it's dreaming of. So here's how you do it. It's a system. After you've made those single bonds for your skeleton, you take all your remaining electrons and you start placing them on the outer atoms first. You fill them up until their octets are full. Now, remember, hydrogen is the exception. It's happy with just 2 electrons. If, after all that, you still have any electrons left over, then they go on the central atom. And this happens all the time. It's a super common problem. You followed all the rules, you placed all your electrons, the outer atoms are all satisfied, but then you look at the poor atom in the middle, and it's still short of a full octet, and you're completely out of electrons. So what do?
The solution is just beautiful. It's so simple. You don't go looking for more electrons. You just use the ones you already have more efficiently. If you run out of electrons, you have to share more. And here's exactly how it works. You take one of those non-bonding pairs of electrons from a happy outer atom, and you just slide it into the space between that atom and the central one. Poof! Your single bond just became a double bond, and now those 2 pairs of electrons are being shared, and they count toward the octet for both atoms. It is the ultimate chemical win-win.
So there you have it. We have all the rules. We have our 3-step process. Let's go back to our water molecule and apply everything we've learned to crack this code once and for all. Okay, let's finish off our water molecule. We figured out it has a total of 8 valence electrons. Our skeleton structure, with its 2 single bonds, used up 4 of them. That leaves us with 4 electrons left over, and according to our rules, those leftovers go on the central atom, which is oxygen. And just like that, it's perfect. Each hydrogen has its 2 electrons, and the oxygen has its full octet of 8. Everybody is stable. The code is cracked. And what's so amazing about this 3-step process is that it's really just the foundation. These exact same rules are the key to unlocking even more complex, really cool ideas, like resonance, which is what happens when a single drawing isn't enough to describe a molecule, or expanded octets, where some of the bigger atoms can actually break the rules and hold more than 8 electrons. So here's the big takeaway. This isn't just a drawing exercise. It's a way of seeing the fundamental logic of the universe. A few simple rules: count, connect, satisfy. And out of that comes the incredible, mind-boggling diversity of molecules that make up our entire world. It really makes you wonder, doesn't it? What other huge, complex systems out there are governed by such surprisingly simple and elegant logic?